And I know that some people from SDSI are joining our collaborations as well. So some of you may have heard the cluster survey name, but we use 200 hours space telescope time and targeting five different lensing clusters: AB370, MAX 1149, 1423, MAX 0417, and MAX 0416, and observe these 5 cluster fields with 3 different instruments. One is NORCAM, and one is NEARIS, and the final one is NORSPEC. And so this is NEARIS GTO program, but in this work, I use the NORCAM observation of the first cluster we have observed, which is the MAX 017. And so we use NORCAM observation plus the ancillary data from the HSD observation. We make a sample of galaxies at redshift 5 to 6. And photometrically selected galaxies at sample of redshift at 5 to 6. And we obtained 123 galaxies at this redshift. The left panel shows the stellar mass versus the SSF plot. And you can see that most of the galaxies are the low mass galaxies with the typical star formation rate. The typical stellar mass is 10 to the 8 solar mass at this redshift. But you can see that some number of galaxies some number of relatively quiescent galaxies are also included in our sample. And having this sample of galaxies, we measure the H alpha and UV flux ratios for each galaxies directly from the SEDs. So the right panel shows the example SEDs in our samples, but you can see that the H alpha is boosting here. This is 40 medium, and this is 40 medium. So we can measure the H alpha flux from the excess in these medium band filters. And we can also measure the UV directly from the this broadband photometry. So we can measure the H alpha to UV ratio directly from the SEDs of low mass galaxy at redshift 5 to 6. So okay, let's move to the results. So first, we noted that a large fraction of gas in the sample galaxies has a very closely paired companion at the same redshift range. So here I show the 6 different positive stamps of our sample galaxies, but you can see that this galaxy has a cross companion here, and this galaxy there is 3 different here, and this is another galaxy at the same redshift. And here you can see 2 galaxies here. This may be a kind of clumpy galaxy, but you can see some clump or some galaxies within this range. And here is 2 different galaxies, and this is as well. And indeed, 40% of our sample galaxies has a cross companion within the 1 arcsec radius, which corresponds to the 5.8 kpc at this redshift. So given the proximity, we think these galaxies are physically interacting with each other. And now looking at the H alpha to UV ratio, this is a distribution of the H alpha to UV ratio, but you can see that this value is widely distributed from below to the above of the equilibrium range we can expect for the steady star formation history. So, and indeed, more than 60% of the sample galaxies has been deviated from this equilibrium range. So these two results should suggest that both of galaxy-galaxy interaction and bursty star formations are quite common in low-mass galaxies at redshift 5 to 6. And this is consistent with the picture of hierarchical structure formation and also the prediction from the cosmological simulations so far. And now we turn to investigating the relationship between the bursty star formation and the galaxy-galaxy interaction. To do that, we divide our sample into 2 different subsamples. One is the interacting galaxy, and the other is the non-interacting galaxies, based on the separation from the nearest neighbor. And here's a plot. And okay, so bottom panel is the H alpha to UV ratio distribution of the interacting galaxy, and the middle one. And the bottom one is the non-interacting galaxy. But you can see that in the interacting galaxies, there's a clear population that is having a very low this H alpha to UV ratio, which cannot be seen in the non-interacting galaxies. This is particularly apparent if we calculate the interacting galaxy fraction for each beam of H alpha to UV ratio, which is shown in the top panel. You can see the clear tendency that this ratio goes higher as the ratio goes lower. And recalling that the low ratio of this age alpha to ratio should correspond to the declining phase or fast quenching phase. Thank you. And the higher value of this ratio corresponds to the fast rising phase. The presence of this low eta ratio population in the interacting galaxy should suggest that the galaxy-galaxy interaction enables the galaxy to experience a really faster quenching that should following the faster rising of the star formation rate. So, okay, so we have to ask ourselves that, okay, we know that the star formation activity can be more bursty under the galaxy-galaxy interaction, but what is the fundamental physics underlying that process? We haven't reached to the conclusion here yet, so any suggestions or objections or ideas are very, very, very welcome. But here, one of the possible mechanisms we have come up so far is the interaction triggers gas inflow into the center of the galaxy. The numerical simulation has shown that galaxy-galaxy interaction or mergers can generate a tidal torque into the galaxy center that makes inflow into the galaxy center. And the inflow into the center can result in the centrally concentrated star formation in the center. And in this case, the star formation rate surface density is really high, so we can expect a really strong feedback from the star formation activity. Then we can expect faster quenching following the inflowing gas trigger star formation activity. And so this scenario must be tested. Okay, I'm sorry. But we have obtained some null spectrophotometry observation, and that is indeed suggesting that these interacting galaxies has a lower metallicity as compared to other hazy galaxies that is observed from the James Webb observation as the similar redshift. And also, one of the crescent galaxies at high redshift universe has been shown that has really compact morphology that is shown in the Strait et al. 2023, but the half-life radius is only 30 parsec, not kiloparsec, 30 parsec of the compact morphology. So these two are indeed consistent with the scenario we have suggested here, but we're gonna test this scenario with a larger sample of spectroscopic observation. Okay, so okay. Thank you very much for your attention.
All right, questions for Yoshi.
Hi, super interesting to see. I read the paper, I remember it, and it's very nice to see actually sparstiness probed in a large sample. And I have many questions actually, but I will choose one. How do you exactly define interaction? Maybe you said and I missed it. So how do you divide interacting from non-interacting? Are we talking about like major mergers, like comparable mass objects, or?
Okay. So we identified a galaxy as an interacting galaxy if a galaxy has a companion within one arcsec radius. So that can be just a chance projection. But we did test the statistical. We did a kind of statistical test to find that the expected number to find a randomly distributed galaxy within that range is less than 1. So I think that the galaxy that is located within the one arcsec radius in the source plane should be physically interacting with each other and at the same redshift. And also the mass ratio. And in terms of mass ratio, indeed there's only a fraction of major mergers, and most of them should be kind of minor mergers. That is, the mass ratio is more than 3 and less than 10. And some of them indeed have a much larger mass ratio, so which should be kind of satellite and main galaxies. But indeed, there's some number of major mergers. And one of the interesting point is that this one. These two galaxies are both 10 to the 6.5 and 10 to the 6.5 for mass, so this is a major merger. So we do have this kind of sample, but there's minor merger as well, and there's satellite versus main galaxy as well. So
yeah, no, this is very interesting. If I may comment on that, because in simulations we do find that this happen a lot, especially at high redshift, and the effect is that the star formation is actually triggered by the merger, so not quenched, but due to, as you mentioned in the end, maybe if I understood correctly, that this trigger star formation can enhance also the feedback and then produce maybe the fast quenching. So I guess that investigating the timescale is the right way to disentangle this.
thank you.
Okay, one more question.
Thank you, very interesting. So maybe just a quick comment that another alternative could be repeated cycles of a burst of a star formation, driving winds, and then recycling of winds can fuel the next burst, and then winds again, recycling, and so that way you may need only one interaction event maybe to trigger the first big burst, and then in simulations we see that quite commonly happen.
Yes, thank you very much. Yeah, I think that's a really good point, and we have been struggled with how we can observationally constrain to see the recycling or breathing of the process, and we may be able to do kind of analyze the duty cycle if we have the larger sample of galaxies, and probably we can do that, but that is work in progress, actually.
All right, let's thank our speaker again. All right, so our next speaker is online. We'll give a virtual talk. So I was wondering if we could get the speaker to Alma to turn the camera on, and we can show them. And if we can show Alma the audience, that would be awesome, so everyone feels included. I'll also note this is the last talk of the day, and there's a small change to the schedule. We will not have the discussion today. Instead, we'll have a discussion tomorrow. And then we shall have beer. Yes. Everyone's excited. And Alma, it's 12 minutes. I will give you a verbal 2-minute warning until the end, if that's okay.
Yeah, thank you. So is my screen visible to everyone? I mean, my slides?
Yeah, we can see your screen. So yeah, are you all ready to go?
Yeah.
Okay, great.
Thank you.
Okay, so I'll just introduce you. So our final talk of the day is Alma Sebastian, who will be talking about the evolution of metal absorbers at high redshift.
Thank you. Hi, everyone. I'm Alma Sebastian, a PhD student from Swinburne University of Technology in Australia, working with Professor M.R.A.N. Weber and Dr. Rebecca Davis on the evolution of metal absorbers at redshift between 2 and 6 using a survey called EXQR30. I'm so sorry that I couldn't be at the conference, but I'm glad that I'm able to present my work online. Elements. Okay, all elements that are heavier than hydrogen and helium, which we collectively called metals in astronomy, were first produced in the universe through the stellar nucleosynthesis processes of the first light sources. These first light sources not only produced these metals, but also ionized the neutral hydrogen, causing the epoch of reionization. So if you are able to study these high redshift metals, that will help us to understand the early chemical enrichment as well as the reionization process. The elements that were produced in the galaxies do not reside within the galaxies, but were ejected into the surrounding gas, such as the circumgalactic medium, through various feedback mechanisms. The circumgalactic medium, or the CGM, is a multi-phase gas surrounding the galaxies, extending from their disk to the virial radii. This gas acts as a source for galaxy star formation fuel and a venue for galactic feedback and recycling. If you are able to, by studying the elements that are present in the CGM, we will be able to get a complete census of the chemical enrichment and star formation rates in the universe. In order to study the elements that are present in the CGM, we use a technique called quasar absorption spectroscopy, where we will search for absorption lines in the spectrum of a background quasar that are being produced by the intervening clouds along the line of sight. And this is a classic example of a redshift 6 quasar spectrum, where you can see the metal absorption lines being detected redward of the Lyman alpha emission line. Adapting the same technique, the Ultimate X-Shooter Legacy Survey of Quasars at redshift 5.8 to 6.6, or XQR30, is a spectroscopic survey of 30 brightest redshift 6 quasars in the southern hemisphere. We have also included 12 archival X-Shooter spectra in the similar redshift range, making our survey the Extended XQR30 or EXQR30 in short. Our survey has high signal to noise ratio and intermediate resolution. The primary aims of a survey is to understand the reionization processes in the second half of the epoch of reionization, to study the quasars in the early universe as well as their environment, and also to understand the chemical enrichment and the nature of the first ionizing sources, which is pretty much of this work. Using data from EXQR30, Rebecca Davis prepared the amazing XQR30 metal absorber catalog, which detected around 778 absorption systems at redshift between 2 and 6. Our sample is 50% complete, or has a 50% completeness limit at an Eklund width of 0.03 angstrom. This catalog has substantially increased the existing sample size of high redshift metal absorber surveys, as well as was able to detect a large population of 131 weak intervening Mg2 absorbers at redshift between 2 and 6 for the very first time. To understand about to analyze the evolution of the absorbers, we use a technique called co-moving line density, or DNDX, which will give you the number of absorbers per unit absorption path length. And for this analysis, we only use those intervening absorbers that are separated from the quasar redshift by a velocity separation of 10,000 km per second. Here you can see the evolution of Mg2, which actually declines from a redshift 2 to a redshift of 5.5. Although there is an indicative upturn at redshift 6, since this data point is associated with larger errors, we cannot be really conclusive at this point. There have been many redshift studies on Mg2 in the past, which actually showed that these absorbers behave differently based on their strength. Also, there has been a work done by Nielsen et al. 2013 on the on Mg2 absorbers at low redshift, and showed that there is an anti-correlation existing between the impact parameter and the strength of the absorbers. Therefore, it is assumed that the weak absorbers are located far away from the weak Mg2 absorbers are located far away from the galaxies, while the stronger absorbers are located closer to the galaxy. Therefore, it is important to understand how the evolution of Mg2 is different based on their strength. Therefore, we also divided our Mg2 sample into weak, medium, and strong. Weak Mg2 absorbers are those with Eklund width less than 0.3 angstrom. Medium absorbers are those with Eklund width between 0.3 and 1 angstrom. And strong Mg2 absorbers are those with Eklund width greater than 1 angstrom. As we can see here, both weak and medium Mg2 absorbers remain constant in their redshift evolution, while strong Mg2 absorbers actually decline in their redshift evolution. We also compare our work with another large survey of Mg2 absorbers by Chen et al. 2017, using data from FIRE, which are shown using the orange points here, and our results are consistent with their work. We also included the DNDX values of weak, medium, and strong Mg2 absorbers at low redshift to get a complete picture of the evolution of Mg2 absorbers from redshift 6 to the present epoch. Then we tried to calculate the cosmic mass densities of Mg2 absorbers, which are dominated by strong Mg2 absorbers, and we find that they actually decline with redshift. We have also included here the mass densities of Mg2 absorbers at low redshift, and we can see that overall the cosmic mass density of Mg2 is in agreement with the global star formation history from Maddow and Dickinson 2014. And also, as expected, the peak in the global SFH do not coincide with the peak with the cosmic mass density due to the lag between the star formation and the appearance of metals in the CGM. Since the results on the evolution of weak Mg2 are first of its kind, it is really important to understand more about the properties of these systems. We looked at their association with high ionization absorbers such as C4 and silicon-4, and we found that the systems with these high ionization absorbers have high column densities of carbon-4 and silicon-4. This indicates that these systems are exposed to strong ionizing radiation in such a way that the carbon and silicon in these systems are triply ionized. Moreover, the systems trace the metal-enriched gas in the CGM rather than the metal-poor infalling gas from the IGM. We also looked at the association of these weak Mg2 systems with Fe2 and found that only 3 of the weak Mg2 systems with Fe2 are iron-rich, while the rest of them are iron-poor. This indicates that most of the weak Mg2 systems with Fe2 retain or obtain their chemical enrichment from the core collapse supernovae of early massive stars in the universe. We not only studied Mg2, but also looked at the evolution of carbon-2 and oxygen-1 and tried to understand what their evolution say about the reionization processes. If you're interested to know more details about this, please feel free to read my recently accepted paper in the archive. Or feel free to message me or ask questions. We also did a comparative study of our results with the recent work using data from JWST done by Christensen et al. 2023. They studied the chemical enrichment between redshift 2 and 6 using 4 quasar sightlines, and there was one quasar sightline which was common to both of our works. In general, our results were consistent to each other, but their work actually detected only 17 out of 43 systems in that common sightline because they missed out many of the weak many of the weak Mg2 and carbon-4 and silicon-4 systems due to the lower spectral resolution of JWST. This emphasized the need of a higher resolution spectroscopy even in the JWST era. Apart from understanding the evolution of the metal absorbers, it is equally important to understand what type of galaxies produced these heavy elements in the CGM. Therefore, using the data from Muse deep fields, we will be searching for Lyman alpha emission lines using software such as LSTCat and then classify them using QT Classify. We did an initial study on the archival data cube J1030 at redshift 6.3, and we were able to recover all the LAEs associated with carbon-4 that were detected in Diaz et al. 2021. So please stay tuned for more results on the galaxy absorber connections. And here I leave you with a quick summary of my talk, and looking forward to the questions. Thank you.
All right, questions for Alma. Questions? Everyone wants to go to beer. Yes, Sanch.
Yeah, nice talk. I'm just wondering, you mentioned the iron to magnesium ratio, and you suggested that most of them are depleted in iron. So could you sort of walk me through like how exactly, if you have considered depletion of iron if you have like made any corrections for depletion onto dust, or if there's like, other handles that we could discuss in terms of figuring out when we only have, just 2 lines?
In this case, what we did was like we just took the ratio of weak Mg2 and iron and we considered those systems with the column density ratio is greater than 1 as the iron rich ones and the rest ones as the iron poor ones. For this particular study, we haven't considered the effects of depletion, to be honest, because we assume that at this high redshift, the effects of dust depletion must be less than that of the low redshift universe. So we haven't considered any dust depletion effects for this work. This is just the ratios of the column densities of Fe2 and weak Mg2.
Thanks.
All right, any more questions? Going once, going twice. Any online? Okay. All right, thanks again for a great talk, Alma. And let's thank all the speakers again. Okay, I would like to remind people, if you are speaking tomorrow, please upload your talks and check that they work before your session. And we will now have ESTAS, which I forget what that stands for, but it used to be a meeting at Space Telescope, and it's beer. So it is a free beer, right? Okay, and snacks. So it's in the cafeteria. So thanks again to all our speakers for all their wonderful talks today, and see you tomorrow.